Okay, so we're going to have a quick talk about signals and filtering, how we convert the analog world to the digital world and back again. As we've stated before, the real world works in analog, and what we need to do is take that analog, the varying voltages, how the real world works, and convert it into a digital system so that we can process it. We then convert it back to an analog form to take some action within the world. One of the other things we need to do with this is we need to do some filtering. Filtering is the way that we select the range of frequencies that we're interested in for this particular process. So, analog world, microcontrollers only work in binary, so they receive their on-off signals. Is the button pressed or not? Is a switch closed? Do we get a number from a particular sensor, like a temperature sensor or inertial measurement unit? However, the world likes the shades of grey, so we need to have various levels. And we need to have a way to convert these various levels into something digital so our microcontroller can do something with it. Now, most microcontrollers have got a device built into them that will convert from the analog world over to the digital world so that we can actually take some action. And these are referred to as the analog to digital converters. We also have a digital to analog converter, but we're not going too much into that. Okay, so on the Arduino, which is the bit that we use to input our analog signals, the pins A0 to A5 are connected up to the ADC. They're down in the bottom right-hand corner, as we can see in this figure. The Arduino uses a 10-bit ADC, meaning it has the ability to detect 1024 or 2 to the 10 discrete analog levels. There's lots of other ones. We can have 8-bit ADCs, which give us 256 levels, 16-bit, etc. All this does is it relates the ADC value, a binary number, to a particular voltage. So ratiometric value, so if we have an input of, say, 5 volts, that's based on the voltage of the board you're using itself, and we have 1023 levels, 5 volts will be equal to 1023, 0 volts will be equal to 0. So this can be simply put as the resolution of the ADC divided by the system voltage equals the ADC reading. That's the number that we get from the ADC, the digital number that comes out, divided by the analog voltage measured. So in our Arduino case, we've got 1023 divided by 5, which equals the ADC reading divided by the analog voltage measured. So that will give us a voltage level out once we rearrange that formula. Now, the way an ADC works, I've just put a little description down in the bottom corner there, is fairly complex. There's quite a few different ways to achieve it in Wikipedia. Always a good place to start, but never trust anything you read there. Wikipedia has a rather good list. One of the most common techniques is to use the analog voltage to charge up a capacitor. That discharges through a resistor. The time it takes to discharge through the resistor is relative to the voltage we're putting in, just through a simple RC network. The microcontroller monitors how long this takes in the number of clock cycles, and that is the number we actually get out from the ADC, number of clock cycles it took for that voltage to discharge through that resistor. Fairly simple, straightforward. It's a common way of doing things, but not the only way of doing things. Okay, so once we've decided on the signal that we're going to input, there's a few things that we need to consider. The first is a sampling rate. Sampling rate is in samples per second, and it must be at least twice the rate of the highest frequency component of our signal. So for example, if we want to read in a speech signal, speech has a frequency component up around 3600 Hertz. This means that our sampling rate must be at least twice that, or 7,200 samples per second. The reason for this is shown in the figure in the top left. If we look at that red line, this is the samples we're receiving in, but the blue line is the signal that we need to see. Now, this is a perfect example of why this is a problem, ideal example, I should say. If we look at the first sample, we're sampling at the peak, at the lowest point of the signal that we want. Our next sample is at the zero crossing point of this signal, but the signal has actually had a great deal more information contained within it than we have actually sampled. So what would happen is our reconstruction of that signal based on the samples we have received would be completely different to the signal that we wanted to actually capture. And this is because we are sampling at too low a rate to actually capture the information contained within the input signal. And we're missing major parts of it as well. Okay, the next thing we have to look at is the filtering. So we've decided on a sample rate. We know we're going to be sampling at least twice the rate of the highest frequency component in our signal. But how are we going to limit other frequencies that we don't want to receive? So again, we look at the voice sample where we have a highest frequency component of 3600 Hertz. We will get clicks, which is a high sort of frequency. We will get other noises in there that we don't want to capture. So we need to filter the signal selectively. And in this, the simple example I've got here is probably the most common, which is low pass filtering, where we put an upper limit on the frequency component that we will accept into the system. When filtering, we have two components. We have our pass band, this is the signal that we will allow through, and we have a stop band. So again, in the case of a speech signal, we would limit our signal at 3600 Hertz, and anything above 3600 Hertz, ideally, would be blocked from getting into the system. In reality, it doesn't work like this, of course. What we need to do is we set our cutoff frequency, or corner frequency as it's called, in our speech signal, 3600 Hertz, and that then trails off, depending on the type of filter we're using, until it becomes a negligible signal. That signal is normally at the -3 dB point of this, the incoming signal, which is termed our half power point. And at our half power point, that is where we define our bandwidth. The signal would continue to come through, but at a much attenuated rate. This also causes a phase shift, which we're not going to worry too much about in here, but it is something that is important as you start to design more complex filters. The way we achieve this in its most simplest form is a simple resistive capacitive network. A resistor is a linear device. It is not susceptible to anything in the frequency spectrum. So whatever frequency we put in, it will attenuate or limit the current flow across the spectrum equally. A capacitor, however, has a high impedance at low frequency and a low impedance at high frequency. So in this case, if we look at the signal in the bottom left corner, we have a resistor which is set to define our corner frequency, and a capacitor which will shunt high frequency signals down to ground. This way it limits the upper frequency components that can actually get into our system. It's a very simple sort of filter, but it's quite effective in limiting some frequencies. The other things we need to look at, and this is where things become very, very complex, is conditioning the signal to suit our application. Now, not only do we have to look at removing high frequency or low frequency noise, depending on our application, through either a high pass or low pass filter, there are other types of filters which enable us to reduce errors within the sensors themselves. Now, this is an example of a inertial measurement unit that we're using in gate analysis. Not only does it have high frequency components which can interfere with our signal and the processing of our data, which we can see by that green line. It has many spikes and lumps and other areas that we're not particularly interested in. We want to smooth that out. But it also starts to drift off, as we can see with the gyroscopic data, that blue line. Gyros drift, and what we do is we create a type of filter, in this case a complementary filter, that uses accelerometer data to correct for the gyroscopic drift and brings the gyro back into line. So it's still a filter, but it's looking at input from other devices, in this case the accelerometer, to correct for errors that we have in the type of sensor, the drift error in this case of a gyroscope. Right, now we'll have a listen to the prototyping instructions, how we're going to put our circuit together, that was created by Joshua, one of our staff, and he will explain how to start putting your prototyping boards together.
This recording shows you how to use components from the Arduino starter kit to set up a basic circuit. This project is number 13 in the book, the Touchy-Feely lamp, so it's a basic capacitive touch sensor. The components you'll need are the Arduino board itself, a solderless breadboard, an LED, two resistors. One is 220 ohm, which is red, red, brown. The other one is 1 mega ohm, which is brown, black, green. If you're not familiar with how a solderless breadboard works, each of these holes takes component pins and jumper wires to connect it to other pins and wires. For example, a pin here is connected to all those alongside it in this row. A pin over here is connected to all those alongside it, for example, and they're separated either side of this channel in the middle. On the sides, a pin runs the entire length of the board vertically, and we see the same over here. This pin is connected to all those others with the yellow dots. So to build this circuit, we'll start with the LED here in the diagram and the 220 ohm resistor. Now an LED is a diode, so it's polarized, which means it's important which way around it's placed in the circuit. The anode is the longer leg, which corresponds to this side on the diagram. The cathode is the shorter leg, which corresponds to this side. That's one way of telling which way around it should go, but also the plastic on the side where the cathode is will have a flat spot, where the rest of the way it's completely round. The flat side is the cathode. So if I place this either side of the bridge and connect this side to the ground like that, then this is now connected at the same potential as all of those points. Now the 220 ohm resistor here, or a similar value resistor, is required so that it limits the current that flows through here, so it doesn't burn the LED out. So we'll connect that to pin 12, which is going to be the pin that activates the LED. So we've now got a complete circuit running from pin 12 through the 220 ohm resistor, through the LED and back to ground. Now we need to connect the 1 mega ohm resistor into the circuit. So if we place that into the board here, and pin 4 connects to one side of the 1 mega ohm resistor, and pin 2 connects to the other side. Then we just have to run this lead out to the actual touch sensor. So I'm just going to run a pretend jumper lead out here, which, if you're using the jumper leads such as the ones out of the kit, you'll have the bare wire poking out of the end. The instructions in the book say to add some foil. You can use something conductive like that as the touch sensor, or you can just touch the bare wire at the end, which will have the same effect of turning the light on. So if we leave that hanging for the moment, then that is the circuit in place. Now you need to upload the code to the Arduino. So plugging the Arduino into the computer, and presuming you've already followed instructions for installing the Arduino IDE, which is the software used to upload code, type this code in from the book, and once that's done, click upload. You'll see the dialog as it's loaded in to the board, and when it gets to this point, it will be ready to go. All you need to do is touch the bare wire at the end of this lead and the LED should turn on. Now you may find that it doesn't upload when you first try because the library that you're including in this line doesn't come as standard with the Arduino IDE. And if you've typed capacitive sensor here, it won't highlight as orange text, and that's a sign that it probably doesn't have the correct library installed. So you'll need to go to the Arduino website, find the capacitive sensing library and download it with that link. You save it on your computer as a zip file. Once you've done that, back to Arduino, sketch, include library, add zip library, and find the library you've just downloaded. Once you've added that, this text should now be orange as it is on my screen, and it has the necessary code to operate. Now this threshold here is the value at which changes the sensitivity of the circuit to touch, so you can reduce this or increase this. In the book it's actually 1000. I'd changed it down to 50 and it's a lot more sensitive. You can actually touch the insulation and it will still come on because you're affecting the capacitance of that circuit by adding your own body in to the circuit and changing the speed at which the capacitor charges and discharges.
Okay, thank you, Joshua. I'm hoping that we won't have to rely on this recording and everything works well with our connectivity, and I can talk you through this in person. This recording will be made available on the thumb drives we're giving you, along with all of the others, and get prototyping. Enjoy. Thank you.